right, how's everybody doing? Good. It's not so hot outside today, but I think it's gonna rain really bad, so that'll be good. So I'll get started with some course logistics. If you remember, we talked about our next 2 weeks. Today we're doing computational complexity part 2. We'll wrap that up. And I plan to do trees on Friday if there aren't any objections. I'd like to give you your class time on Friday. Object. Then you can come visit me in office hours, and we'll have our own class. But no, I'll send out on Canvas Friday morning the summary review of what's going to be on the exam. I'd like you to take either this class time or some time over the weekend to look at it, see if you have any questions that are specific, so that on Monday we can both go over it, we can answer any questions you have, and we'll do practice questions at that point too, so you'll get to see the format. That's our schedule. I figure you probably don't want to hear about trees if we're not going to test on trees, so we'll start doing trees after the test. So, last time we were talking about computational complexity, and we started thinking about it kind of at a conceptual level. So if you remember, we had a few different ideas about how we could measure how efficient an algorithm is, how complex it is, and we primarily were talking about runtime, like how long does it take to run. And specifically, we want to relate that to the size of an input. Usually, it'll be like the physical size of an input, so like the number of items in a list, maybe. And we want to get a relationship between that input size and the order of growth in terms of the algorithm's runtime as that input gets larger and larger. So we really care just about very large inputs. So we started with this idea of maybe we could empirically measure things, which is not a bad idea, but we got all this noise in that kind of measurement, right? So it depends on the computer you're on, it depends on the operating system, it depends on the details of the implementation of the algorithm. It just makes the task a lot harder to do. Doesn't mean it's not practical. Sometimes, one case where you may have to do this is if you don't have access to the code of the algorithm that you're running, right? If it's literally a black box, then maybe empirical testing is the best you can do. But in most cases, you'll be writing the code or you'll be looking at code and you'll be able to go through it and see, does it loop over all of the items in a list? Does it do a recursive call and divide the list into pieces and then do something with each piece and then put it back together? So all of those things you can't really consider in an independent way if you just do the empirical measurements. So we talked about, after that, doing counting operations. So the idea there was we have a piece of code, and we all agree that there are some primitives, some primitive operations, some fundamental things like adding, subtracting, saving a value, retrieving a value. And we give them each a value. We'll just say they each get 1 as a value. And then we just count up how many operations will this code do based on an input size. And this was a little bit better, but it still kind of depended on the exact implementation of what was going on. So you can make choices as a programmer that would have more operations or less operations, and they're really not important to the actual algorithm that we're studying. So an example of that we looked at was this array sum function. So we had an array A with length n, and we said, okay, we're going to make a function where all we do is go through the array, add it up, store it in this variable sum, and return sum. And so we came up with, this is one operation, this is 1, this is 2, this is 1. And then if we look at it and think about how this will execute, depending on the size of the array, right, we're always going to do sum. We're going to do that once. And we're always going to return once. But these operations will depend on the length of the array. So we'll do those n times, where n is the length of the array. And that let us come up with a formula like this. And so that was nice, because now we can take different algorithms, do this, come out with 2 formulas, or however many formulas, and compare them. So counting is very good, and it is kind of the way that when you look at an algorithm to analyze it, you can think about it that way. However, we don't want to count things that don't matter. We only care about the operations that take the most time, what we'll call the dominant operations. So we move to what the standard is in terms of analysis of algorithms, and we're calling it order of growth. And the idea is that what we really want to do is relate the time or the resources needed to the size of the input when the input becomes very, very large. And so we don't want to consider any of the specific implementation details that don't matter. We want to ignore anything that doesn't depend on the input size, right? So any like temporary variables or things that just happen once, those are negligible. And we want to measure everything in terms of some input. And so typically that input will be represented as the letter n, which is why you'll see, order n squared, but that's just convention. It could be anything that we use there. And so this is what we'll look more at today, is this order of growth approach. If you'll remember, there are three kind of major cases that we care about when we analyze an algorithm. So thinking about like an array and say we want to search the array for a value. Well, in the best case, the first element of the array is the value we're looking for and we're done, right? Easy, really quick. So that's kind of uninteresting. That's like, you're lucky, and that's great. The average case is to say, let's take all of the possible inputs and all of the possible things we're searching for, run them, and get an average of that runtime. And you can see why this is difficult. Now, this matters a lot in like practical applications, right? There are sorting methods that have great average cases. They don't have the best worst case, but the average case is good enough that they're used in a lot of scenarios. So average case is something where you can sample, you can do different things to estimate, and it does have its place, but it's typically not what we do in terms of analyzing algorithms that we're looking at that are written down. That may be something where more measurement comes into play, where you care a lot about the distribution of inputs and how they affect the runtime. And so it gets a little more complicated. It's kind of a whole extra step on things. So what we're going to focus on in this class, and what you'll mostly focus on in your other computer science and math classes, will be worst case analysis. So this is the worst possible thing that could happen, right? So we've got our array of numbers. We're searching for a specific number. What's the worst thing that could happen?
It's not in there? Or it's at the end?
Right. Either it's at the very end or it's not there at all. So you had to go through the whole input in to see if that was the case. And so that's what we care about. And we care about that when n is very, very high. So big O notation is what we talked about last time. It's written with an O, big O. Pronounced big O. Things to remember, in general, we don't care about any kind of constant factor. So anything that only happens a set number of times and the input doesn't affect it, we just ignore it. We also don't care about lower order terms. So if there's an operation that happens, say, n squared times, and then there's an operation that happens n times after that, we only care about n squared because it's much bigger than n. And so that's why we focus on the big inputs, right? Because that's where that becomes obvious. So we discussed these dominant terms and looked at a few just basic equations and how you choose the dominant term. And so like here are some where n squared is the dominant term. Here's order n log n, 3 to the n. It's a pretty simple idea. There's a few cases that can be a little bit confusing. So let's try these. This first one, what is the dominant term in that one?
N squared log n.
Okay.
Not changing numbers.
Change your mind?
Third.
Yeah. So yeah, into the third there. So for me at least, these are always the trickiest. I tend to think that they're bigger than ones that they aren't. Kind kind of, everybody has their own thing. But yeah, so n to the third is the term that as n gets very, very large, so think about it like a limit or something as it approaches infinity, essentially. That's the term that matters the most. That other term is going to just become tiny in comparison. Okay, so the next one, what's the dominant term?
And,
Yeah.
Yeah.
because you said log n was between 1 and 2 or something like that?
So it'll depend on the n. I mean, it's just taking a logarithm of it. What's important here is that it's less than n. So it really could be any function that's less than n there. And also, you can take logarithms of different bases, right? So typically, we're doing a base 2 here, but you know, any one of them would still hold to this principle. Okay, how about this next one?
It's going to be the one on the right.
Yes, it's x. And see, we can change the letters, isn't it cool? Yeah. No, I just want you to know that the letters don't really matter. You'll usually see n. We can put whatever you want. Okay, the last one.
Is it going to have two different ones? Or we're going about half the exponent altogether?
I don't know.
All right, we're going about half the exponent altogether. So it's the third one. The last one? First one? No,
It's the exponential. 2 to the n.
To the end?
Yeah.
Yeah, so it depends, right? It definitely, if these were all the same letter, right? Like if they were all x's or all n's, 2 to the n. But here we've got 2 different letters. So this is a little more realistic, right? How many algorithms only take one input that only, you know? So you can analyze it in terms of a variable. And I mean, this is kind of like similar to calculus or anything where you can like say, okay, I'm going to differentiate in terms of this variable, even though there are multiple. But here, yeah, you could say, well, in terms of the x input, this term matters, and in terms of the n input, this matters. And so, yeah, that's just something to think about. It's not always just a simple one input thing. Okay. So today I want to start by looking at these common computational complexity classes that we have. So this has just been plotted out for input size over operation count. And these are the different classes. And again, these are just the ones that are traditionally the ones that we care about the most. There are things in between that can matter for very specific things. But these are what we care about quite a bit and what shows up when we analyze things. Our wonderful projector doesn't do a great job of rendering this color, but what I'd like you to notice is that these lines, at least at the beginning of this graph, kind of cross over each other. And if you see, this is 2 to the n here, and actually into the third is higher. And so something to remember, you got to zoom out. So we always care about the input size being very high, right? At the beginning, when the input size is low, certain functions may be more efficient than others, but that's not the case as the input grows. So we care about very high inputs, and as you can see, that crossover does happen for those two, and then everything's ordered as you would expect. And so if you zoom in kind of, you know, right where everything starts, you can see there are several crossovers here that are going to occur. And this is just plotting out those base functions. And so when you have something that has like constants in it, whether it's some constant that's added or multiplied, it will offset these lines, right? I mean, just like it would when you're plotting any function. And so you have to be careful to always make sure that you've gone far enough to see any crossovers that might occur. Okay, so I'd like to define big O a little more formally than we did last class. So I think we can work through it with kind of an example here. And so let's just pretend we have a piece of code that we've analyzed, and we find that this is the function that represents it, right? So 4x squared plus 4x plus 1. That represents how our code runs. And so here's a graph of that. You can imagine this is the input size, and this is some measure of resources or operations that are taken. So what we want to do for big O is we want to find an upper bound. And so we'll traditionally call our function f of x, and we'll call the upper bound function g of x. And the idea is that we want a g of x that we can find a constant, a pair of constants, that we can multiply g of x by, and it will eventually exceed f of x, right? Because we don't, at the low end, things might be different. But as the value of the input gets higher and higher, is what we care about. So as that limit goes towards infinity, we want a function that will exceed this function. So, ideas about how to do that.
We want one that's gonna be bigger than that.
Yeah,
You want one that's going to exceed it, like it's gonna start lower and then get higher.
it could start at the same or higher, but it could also start lower. It just matters that at infinity it gets higher.
I think it should go up in the spectrum on the x-axis. So like it started at 0, so the next one will be bigger if it starts at 20 or 40.
But what if I only have like 15 as my input?
You just put the exponent,
What?
where's the exponent?
Yeah. So based on the terms that we've set out so far, right? Why don't we just pick the highest function we can think of? That would satisfy it. So what we could do, let's say we're not just going to give the wild answer that's just like pick the highest thing you can think of. And we'll talk about why that's unhelpful and what we do about that. But you could start, you could just say, okay, let's just choose x, right? Which, just increases with the input, right? And this graph is scaled such that you can't really see it, but trust me, it's increasing one at a time. So does x meet that criteria, though? Does it ever exceed this? No. So that doesn't work. Okay, x squared.
It doesn't, but it's getting there.
Getting there, yeah. 3x squared.
I think it beats it. Nah, it's not curving up enough. It's not-
4x squared. 5x squared.
Still had to guess.
Nah, I think one more
I think one more.
for safekeeping.
Look at it. Things to go back. So 5x squared would work, right? It's bigger. You can see that it doesn't start bigger, but as we go to infinity, it gets bigger. And you can just think about it. You can look at these numbers and plug things in and test that out. So, if we're going to formally suggest this, what we need to do is say that 5x squared is going to be greater than our function 4x squared plus 4x plus 1 for all x's that are greater than this value, which is the crossover value, right? So what we can do is we can set g of x to this, and we can say that it will always be greater once we pass this specific x. So now it's an upper bound on our function. So the formal definition here, we can say that the function f is of big O g of n if there are positive constants, and we'll call them C0 and N0. You may see them with different names. It's not that important. But the relationship that has to be maintained is that our function is less than or equal to the C0 constant times g of n, which is the thing that we're arriving at, in our case, n squared, right? And it has to be that way for n greater than some value. And in our case, we solved that intersection to get that value, right? So here we'll do another example that is a little bit more manageable without like graphing it out or anything. So assuming that our function is 2n plus 10, we can look at that and kind of based on our intuitive understanding, what is the big O of 2n plus 10? N, right? That's the dominant term, right? 10 doesn't matter, multiplying by 2, whatever. N is the thing that drives it. But how do we prove it with this framework, right? So in this case, we can choose constants. And you can take a methodical approach here to choosing these by solving things. But you could truly just kind of start guessing and work your way to them if you wanted. In this case, C0, we're choosing 3, N0, 10. And so this is how that works out. So we've got our function f of n, which is 2n plus 10. And we need it to be less than or equal to our constant C0 times g of n for all values that are greater than n of 0. So if we come in and we substitute in this value, right? So we put in our function here for f of n. We put in 3 for our C0, and we put in n as our g of n. We can solve that, and we get the crossover value of 10, right? And so then we can choose 10 as that value where it crosses over. And so this is kind of the heart of it. This is how it's defined mathematically. This is how you can prove it. Most of what we do, and what I've ever done, is more intuitive. It's things that you can look at code, you can kind of annotate things and see where the dominant factor is. And there's not necessarily a lot of need to remember the exact letters that we're using here or that kind of thing. The concept is what's important, is that it's a boundary that is above the growth of that function. And so here it is graphed out. Our function is in blue. And so we can see that 3x crossover and always be above it. Now, we've also got x down here, which is always below it. And that is also something that's pretty important. So, and we already got to this a little bit. So if we say, in that first example we worked, where we had 4x squared plus 4x plus 1, and we said it's big O of x squared, right? X squared is the dominant term. Is it big O of x cubed? So we know it's big O of x squared, right? X squared is always going to work for us. If something's big O of x squared, is it also big O of x cubed?
No.
Yeah, it is.
Why?
Because big O is an upper bound, right? So just like we talked about earlier, we could pick anything higher, right? So this makes big O itself maybe not that useful. And so it's interesting that big O is the thing we think of. It's the term that's very popular when we talk about this. But big O by itself is just an upper bound.
So I mean, if it's less than x, big O x squared, then it got to be less than big O x cubed.
So if x squared is an upper bound of something, if it's always higher than our function, well, x cubed is always bigger than x squared, so it's also always bigger than our function. Yeah. And so you could imagine scaling that out, right? So what am I really telling you? And that's big O is not really enough. When we think of big O, we tend to think that it is a bounds that comes from both sides, but it's not. Big O is just the upper bounds. So you can always choose a very high upper bounds, and as long as it's the actual, above that actual function, it is a valid big O choice. So that's why what we really care about is big theta. So big theta solves this problem because big theta is both an upper bound and a lower bound on a function. So it tightly contains the function, which makes a lot more sense because we care about that. We don't want to just always say, oh, it could just run forever. And yeah, technically that's right, but what we care about is being able to actually say, this is the closest upper bound, the tightest upper bound that we can have for a function. So what big theta does is it says the same function that we choose has to be both an upper and lower bound, which sounds a little bit scary and impossible at surface value maybe, but it's not. So all we have to do, we take that same big O criteria we had, right? And we chose those two constants that made things work for us. Let's just pick two more constants. And we'll call them C1 and N1. And what they have to do is the opposite. So we have to find two constants that would allow g of x to always be below our function as n becomes very, very high. And that's something we can do. So if you remember our example of the function 2n plus 10, right? So for our upper bound, our big O, we chose 3 and 10. And we were able to show that that works and gives us our g of x being n, right? So g of x is n, and these two constants will give us something that is always above our function, eventually. If we choose constants differently, in this case 1 and 0, right, which we saw on this graph earlier, we can make the same function, n, stay below our function. And that's what we saw here, right? So our function, this middle one in blue, our upper bound, 3x, the lower bound, x. So big theta has us come from both directions at this. It's a little bit to think about, but it can be done. It's just a couple of equations and 4 variables, and you could solve it. And you can know if the g of x that you're choosing actually works or not and satisfies these criteria. So you can both know if you've chosen something that is too high, right, that the lower bound doesn't work, or something that's too low where the upper bound doesn't work. And so that's what we care about. We want to get as close as we can to that actual function that we're trying to analyze. So that's big theta. And just the thing to take away is that big O is only the upper bound. So if you're ever asked, if you're ever told something is big O of x or big O of n, and then ask if it's also big O of n squared or x squared, yeah, it is. Big theta is the one that comes from both sides. It's a more strict definition. So a couple of other things that we want to think about that come up in code quite a bit when we're analyzing things. So here I've got just some arbitrary for loops, right? So we've got an array input of length n, and all this code does is it has a for loop that prints out all of the elements. There's another for loop that prints out the elements times I. And so what?
A or R?
Array.
Okay.
Yeah. So yeah, and again, when we're looking at this kind of stuff, you'll see lots of pseudocode that's not real code. You'll see things that are kind of just, it becomes more mathy. You can pick variable names. You don't have syntax. You don't have all of that. So here, what is, and I'll ask the big theta this time, of this, if the array input size is n.
If the array is size is n, what's the big theta?
Mm-hmm.
Is it 1? Or
Nope.
0?
Nope.
I only see 2 numbers.
So we come through, we run through this first loop. How many times do we go through it? N times, right? Then we come through this loop. How many times? N times. There's no trick here. Each of them are going through the array, right? So we could say this is n plus n.
So n squared?
2n, though. So these are one after another, right?
Oh, yeah.
So 2n. And what's called the law of addition for this tells us that if we imagine this code broken up, right? Just pretend we're just analyzing this alone. This is in. That's easy. We analyze this alone. This is in. When we have them together and we add them, we can essentially add the two big thetas here, which means that the overall big theta of this is in, because the 2 doesn't matter. The 2 is just a constant. And so when you see loops that are like this, just one after another, loops in series, we can call it, you don't need to do anything special apart from analyze each one, and that's just an addition term on your function that you're doing.
So it will be 2n, but we just gonna make it big theta n.
Right.
So if it was 5n, it'll still be big theta n.
Yes. Yes, it would. Yeah. So, and the reason is that we don't care about any constant. Like, a number that's being multiplied is negligible for this. Yes?
What case would it become a higher in power index?
Yes, I'm glad you asked. Okay, so imagine, instead of putting those loops one after another, right? We have our first loop, and then inside that loop, we have the second loop. So now if we think about this, we're going to run this loop n times, and each time, we're going to run this loop n times. So now, rather than add these, we multiply them. And now, that brings us up to n squared. And so, formally written, it's just like this, and it's just saying, if you're going to multiply things that are of this order together, then this applies. You know, you can analyze them together or apart and add them, but it's, or multiply them, sorry. This is where you start to get the higher than n, right? Higher than just the number of elements in the list. And this is probably like the most classic example you will see on anything, right? Is nested for loops. You want to nest another one, you can add more to, you can keep going with that. And that's because to get to some of the things that are more complicated than just, you know, like n to the second, third, or whatever, the algorithms become a little more complicated in general. But they are all things that you will study at some point. I think, yeah, pretty much for every major in here. Yes? For big theta? So you need, what you're looking for is the g of x, right? Now you need two sets of constants to prove it, but it will be the same g of x. And so that's why, yeah, it comes out with just one. So that you have that g of x on one side and you check it with constants, and on the other side you check it with constants, and if it works on both, that's it. Yeah, that's a good question.
So big theta, I guess, would be defined as some function who we could give a constant to be an upper bound and a different constant to be a lower bound.
Yeah, yeah, that's a fair way to put it. Yeah. So, and big theta is usually the thing that we're actually thinking of when we say big O, because it's what makes sense, right? We want to get very close to it. We don't want to just make like very high estimates for no reason. So these are kind of the practical things. I think in analysis of algorithms, you'll deal with things like recursive calls and recurrence relations. And so obviously we have code that will break things up into pieces and do operations. And so that becomes a little bit more complicated to analyze. It's not that complicated. We just won't cover it in here. But do know that there are ways to do that, and I'm pretty sure all of you will learn that if you haven't already in an upcoming course. Other questions on any of this? Okay. So in terms of what we'll need to know in here, we won't need to know the formal proof. You won't be asked to like prove this with the notation and everything. More so, we'll look at things like a piece of code like this, and you'll look at it and essentially do kind of the operation counting and maybe come out with a formula, or maybe look at a list of potential choices, look at a graph that shows them, and choose what's correct for the function. But it's good to be aware of this. It's something that you'll continue to develop, and it can be really useful. All right, so that is all that we're going to cover about computational complexity at this point. We will talk about it more as we get into other data structures. We'll relate it to those data structures. So don't completely delete it from your mind after the exam, because you'll need to remember it just a little bit. That's all I have. Friday, I will post the review. Please take at least 50 minutes to look at it, think about it, and then we will meet on Monday and discuss it. Please enjoy the concert if you are going.